work to your attention. A lot of the stuff we're talking about, he's had research about. Anyway, not that much. All right. So this is the number of training examples, and this is your error, right? And you want your error to be like it's 0, right, in a perfect world. And almost every technique we use, as we increase the data, as we increase our training data, our error is going to go down. Does that make sense? More knowledge, kind of do better. But the question is like, well, if you're doing naive Bayes versus logistic regression, like which model do I pick? And in this paper and a lot of people didn't really know. Like, so this is what everybody does, like in practice, is they just try them all and sort of assess how well these different algorithms work on your data. But what this Michael Jordan and Andrew Ng paper did was try to investigate this question theoretically. When do we expect different types of models to work better without actually having to do all the work of implementing them? And if we could figure out these expectations, then we can decide which one is likely to work and try it without having to explore the entire space empirically. So if you have, so if this is like naive Bayes, typically logistic regression will do something like this. So both of them asymptote out, right? But logistic regression, let me label them, LR and B. And this is a general pattern for generative versus discriminative. So as I add more and more and more training data, my discriminative model is going to tend to perform better than my generative model. Why might that be? Intuitively. Yeah.
Is it because naive Bayes makes a lot of independent assumptions, so that as you increase the number of examples, you really can't escape those assumptions you made?
Yeah.
The logistic regression doesn't make assumptions.
Yes, that's exactly right. So this model is making more independent assumptions than this model. So even though we got to the form of logistic regression by deriving it from the naive Bayes independence assumptions, when we actually estimate these parameters, we're not relying on those independence assumptions. We're just directly finding the parameters that minimize the misclassification rate. So we're making fewer assumptions with this discriminative model. So as the data tells us more and more, and we just let our model fit to the data in the best way that we can, eventually we're going to get to a lower training error than naive Bayes. So why might naive Bayes perform better? Why might your generative model perform better when you have less data? It's sort of the inverse reason from what you said, from what he said. Yeah?
Well, you could have like a lot of different features, and like you may not have like every combination, so you could end up with like 0 probabilities for you.
Well, you had the same features in both of these.
Well,
Does that make sense? Yeah.
when you're testing
Yeah.
data, right? Like you don't have every example, so if you don't make assumptions, you have to calculate probabilities for every single case unless you make a naive Bayes assumption.
Yeah, right. I think you're getting to it, right? So the basic idea intuitively is that you are making assumptions, and they're not totally wrong. Like they might not, as you get to the limit, like you can see that there's a difference. But you're using, like basically the naive Bayes assumptions are letting you use less data for more power, kind of. Because you're putting your knowledge, like you're saying, I'm going to assume things factor in this way. I'm going to assume these features are independent. And if that isn't a completely terrible assumption, it's going to give you more power when you have less data. Eventually, if you get more data, this model that's kind of making fewer assumptions is going to outperform it. But when you have fewer data, the knowledge that you put into the system can make things work better. Yes?
Will the assumptions you make with a naive Bayes make it less likely for you to overfit your data?
I don't actually know. I sort of know from hearsay that conditional models tend to generalize better, but I don't actually know the answer to that question. I can take a look and see. I'm trying to think about it. So I do know that naive Bayes tends to overestimate the probabilities of the data. So it'll give you a probability out, but it'll tend to make them very close to 0 or very close to 1. where logistic regression will tend to better tell you when it's not sure by giving you a probability that's close to a 0.5, if we're thinking about binary classification, which we mostly do. Yeah?
The error here is the training error.
This is the testing error. Yeah. Okay. All right. So did DK talk about that? Good. All right. All right. So I think this is important because it's sort of telling us when we might use which models, and we're going to sort of keep pushing on this as we talk about support vector machines. So support vector machines are in this third category, sort of pure machine learning. We're going to directly estimate our classifier function rather than going through the intermediary of probabilities. So it's kind of like one step more in this direction in terms of what we're trying to do. And there's actually a lot of things hiding in here. So we were actually thinking about covering, I wanted to cover one of them. We were thinking about decision trees. But I think SVMs are they're kind of the state of the art of machine learning right now. Maybe deep learning is too, but anyway, they were the state of the art for a long time, and they're a very popular method. A lot of people use them, and they tend to work very well. So, whereas decision trees aren't cool right now. Doesn't mean they're not cool forever, but I sort of figured it'd be fun to do the cool one. All right. So like a decision tree would basically be learning how to would basically learn these bunch of conditional statements. So have you guys done the project yet? You guys are maybe mostly started it. Some of you are nodding. So we had you guys do, one part of it was to hand code a classifier, right? Where you just kind of had to write a little Python program to classify the email. So decision trees are kind of like that, only they're trying to generate the code automatically, directly. So that's the representation that they're using. And there's sort of a bunch of rules and algorithms for splitting on different things. So SVMs are sort of staying in this family of what people call linear models. So this is sort of saying this is my classification function y of x, and I'm going to take some features, phi of my input data. I'm going to dot product it with some feature weights. So this thing is going to be a scalar, and then this is a bias term. So that's going to bias me towards one class or the other. Sometimes when people write this, they stick the bias term inside, like they make a special feature that's always on, and then they stick the bias term inside the weights. Other times they don't. I think the reason is largely historical, and the book I was using for this had it, so that's why we have it here. SVMs usually used it, logistic regression has it, but often doesn't make it explicit. So then your classification function is basically the sign of this. So here we go. So f of x, my function is going to take the sign of y of x. If it's positive, I'll return class 1. If it's negative, I'll return class minus 1. So sort of hard to argue with. Any questions about that? This is a setup for naive Bayes, and this can be used to set up naive Bayes and logistic regression as well, with exponents and stuff. Okay, so here's a picture of what this might look like. So you have some points, some positive points and negative points, or negative points and positive points, depending on what you might like to pick. So how can we decide what decision boundary to use here? So decision boundary is going to be a line that we're going to draw. Maybe I'll draw this on the whiteboard so I can actually draw some lines. I wonder if I have different colored. I don't. Oh, I do. Okay, good. Different colored markers. Okay, so I'm going to draw my axes, and this is x1 and x2. So I'm going to have a two-dimensional feature space, so x1 and x2. And then I'll just draw some points here. And then I'll draw some more points over here. All right, what's a good decision boundary for this? Yeah, okay. So here, I wish I had a third color. Harry, can you mind running to the supply room? And Jeannie has the key, if not. Oh, perfect. Oh, good. Never mind. Thank you. All right. All right. So I could sort of draw. Harry, do you mind running anyway? Because this is dead. Okay. Jeannie has the key, and there's a box right around the corner. Thank you. All right. So this marker is dead. Hopefully you won't get confused if everything's green. So I can draw this one. What about this one? Yeah? What about this one? There's lots of them. What about this one? Yeah, so our training set doesn't really tell us which one is better than the other ones, okay? So why might we think about curly lines versus straight lines? Do you guys think the curly line one is good or a straight line one is good? Straight, why?
Math faster.
Maybe, yeah.
Generalize better.
That's getting closer to it, yeah. Why might it generalize better?
This model is simpler.
Yes, the model is simpler. So I'm not, a curly line would be consistent with my training set. And there's obviously an infinite space, right, of possible decision boundaries I could use from this data. Machine learning is an under-constrained problem. But I prefer a straight line because that makes the model simpler. And that often makes it generalize better. I don't want to make any, thank you. I don't want to make any assumptions that aren't actually warranted by the data. So that's sort of the linear version of the classification. On the other hand, I might know something about the world that makes me want something more complicated. And we'll talk about some examples where that's warranted later on. So that's sort of this sort of intersection between what we're letting the data tell us and what we as engineers and computer scientists bring to the table and put our knowledge into the problem. So we might think it really is curvy, and then we might decide we want to use a quadratic decision boundary, for example, or a cubic decision boundary or something else. And we'll talk about how we can do that. Okay, so the SVM intuition is that we want to choose a straight line, and we want to choose one that kind of separate this versus, let's see, this. So which one do you guys prefer? This is 1, and this is 2. 1, yeah, why?
More evenly separated.
Yeah, so if this is my decision boundary, let's say this is coming from a Gaussian centered here, what might happen when I come to test time and I get a new point? Yeah. Yeah, it might cross my boundary and be misclassified. Yeah.
Sorry, is this the training set right now? Like we already know all the reds, the blues, or greens?
Yes, this is the training set. No, I need more colors. And then this is but I'll draw so this point, let's say that this point that I've just drawn now is a new point that's in a test set, and it's red. Okay, so if my decision boundary is here, I might misclassify it. Whereas if it's in the middle, then I'm sort of more likely to get the right thing. So that's like the thing that an SVM is trying to do. It's trying to find the decision boundary that's far away from all the points in the training set. So that if something's wrong, if you get a new point that, like it's sort of saying, well, new points are probably going to be close to the existing points. And if I'm far away, it's more likely I'll get the new points right. So what this is, so here's the sort of slide version of this. Why might you not want these? So the SVM idea, so this whole thing of like, I want to be far away. People talk about this a lot in machine learning, and the jargon word for it is maximum margin. Okay, I want the margin is like the distance between my decision boundary and the points in my training set. So this is a picture of it. And they have these circles here. This is, I don't know why they call these things what they call them. But anyway, these circles are called the support vectors. So what these are is the points that in the training set that are closest to the decision boundary that it inferred. So I think I have a little thing up here. So these support vectors are what it's actually using to figure out where the decision boundary should be. So and it kind of arises like if you have like this is how you pick the boundary. You have to be equidistant between your closest points, and that's sort of what happens. Okay, so that's sort of the intuition behind support vector machines. The math of this is kind of crazy. I don't know if it's really crazy, but we'll talk about what this actually means. So this is sort of mathematically what I'm trying to find. So I'm trying to find W and B, and once I have the W and B, that specifies this decision boundary. Y equals mx plus b, right? So this is in 2D, of course. In general, it could be larger. So here we're talking about lines. In general, it'd be a hyperplane, like a n-dimensional plane in space. Yes?
So for this, are the features just an x value and y value?
Yeah, it's actually an x1 and an x2, the notation I'm using. And then the y is the class, but yes, that's right. So here there's not really features. In a lot of machine learning, they just assume that the x is already featureized. So that's usually a lot of magic happens to get to that point, but we'll just sort of say we've got it. All right, so this min over n is your data, and t sub n, I think I have actually this is the same stuff with the legend here. T sub n is your class, so it's 1 or -1. And this thing in the middle here is how I'm going to get to my classification function. So it's the weight vector crossed with the features of x. So in this case, it might like if they're in this example, it'd just be an identity function that returns itself because it's already featureized. But in general, you could have it do more complicated things. Plus your bias term, and you're trying to minimize over all of your data points. So as you change w, the specific point that gets highlighted here is going to change. So as you imagine kind of moving around with different w's, the minimum value is going to be different, and the one that globally minimizes over everything is going to give you this one here. So to solve this, so this looks hard to solve, but actually there's like a trick, and the trick is Lagrange multipliers. So I'm not going to talk about the Lagrange multiplier version of this. You can go read in the textbook. The book I recommend you read if you're interested is and I've actually drawn. I should actually put a link to it up there. I've been drawing from the Christopher Bishop book, as well as from Russell and Norvig, because the Bishop book has, I think, a better exposition of the machine learning of things, and it'll actually derive like where this all comes from. But basically, you switch to the space of these A's, and then optimize this. It's what's called a quadratic programming problem, and magically, it's efficient to optimize. So Russell and Norvig just completely skips over. They don't even say the word Lagrangian. If you read in the Christopher Bishop textbook, they derive it and show where it comes from. So this is another. So I don't want to like go through the whole derivation, but I do want you to not be scared of this. So if you need to know, it's just a bunch of algebra, and you can kind of go and figure it out. Like what they're doing is relaxing the problem and then adding some constraints to get you back to the original problem. And these alphas, you can write the w's and the w's and the b's in terms of these a parameters. And the math, you have to trust me that the math works out. People call this the dual representation. And it's one of the two tricks for making SVMs cool. So the reason this is nice, and we'll talk about we'll talk about that. We'll give an example of that next, is that we don't actually need to compute our x sub n's, our phi's of x sub n's to do this. The only thing we have here is the dot product between our feature vectors. So one way of computing the dot product is to actually compute our phi's of x sub n's and then dot them. But very often for different spaces of features, this dot product can be computed directly without going into this feature space. So when that can happen, this dot product of the feature vectors can be replaced with a kernel function that basically corresponds to doing the dot product directly, and then you never need to compute these phi's, and that means you can use really funky ones. I'm really sorry. Sorry about that, guys. Turn it off. All right, so you never need to compute the space directly, and that lets you work in interesting feature spaces, and we'll see how that can pay off in an example. So the basic take home of this is, like many machine learning things, there's a trick to take this difficult optimization into one that we know an efficient algorithm for. And the book just says there exist efficient quadratic programming packages. I looked around in Python. There's actually not that many good ones. But most people who want to use like SVMs, they just use an SVM library directly, which has inside of it a quadratic programming problem. So we basically know how to do this. Okay, So what I wanted to talk about next was sort of this idea of the linear decision boundary. So, and compare this to the boundary that would be inferred from logistic regression. So this is another classification example with SVN. These are basically two Gaussians here and here. And this is showing, just like before, the boundary that an SVM would give you and the support vectors that it would find. And compare this to the logistic regressor trained on the same data. And then both accuracies are from a held out test set. So you can kind of see that they are actually giving you different classifiers. So the logistic, and the difference basically is the SVM is only using it's picking out those 3 points, so that's kind of using all the data. But it's getting the line only from those 3 points, whereas the logistic regressor is trying to sort of use all the data in the training set in order to come up with its decision boundary. So you can actually write down the different error functions. It's basically, what it works out to be is sort of one more step in the generative model, discriminative model, and these sort of pure classification models, where you're really, so logistic regression is trying to capture the data, right? So it can give you a probability. Whereas SVM is really just about trying to minimize your error on the classification set. Okay, and which one works better it sort of depends on the details of your data. I actually wanted, maybe I'll do this for next class. Like I wanted to go and dig and see what we know about the difference between SVMs and logistic regression. Similarly to what we were talking about with naive Bayes and logistic regression. So we could sort of understand theoretically when one might be better versus the other ones. But this kind of just shows you that they are different in terms of the thing that you're trying to minimize. And that arises from the different error functions that you're working on. So the maximum margin condition versus maximum likelihood of the conditional distribution in the logistic regressor. Does that make sense? Okay. What other things might we like to minimize when we're doing this? Like max margin is one. Number of misclassifications. Yeah, so we might just directly want to minimize the number of misclassifications on the training set. So what that would look like is it would be back to our under constrained case, right? So we would have lots of models that would work to minimize the number of misclassifications. And what people do, like lots of these are still under constraint, is they'll do something called regularization. So they'll say, I want the simplest model I can find for some definition of simple, and they'll use different definitions of simple. I want the simplest model I can find that minimizes the number of misclassifications. And sometimes, and when you have these feature weights, the people call this regularization, and simple, there's sort of two common ones that people use. One is the squared, like the sort of, it's basically the magnitude of W sub I squared. And I try to minimize this. I'll just add it on to whatever data-driven function I'm trying to minimize. Or you can use the absolute value. So one is curvy and mathematically nicer because it's differentiable. So when you stick it in your math and you take Lagrangians and do all this stuff, it kind of works out better. And one, absolute value is like this. But mathematically it's less nice because you have to have this like if it's greater than 0 and if it's less than 0. But both, and the absolute value one tends to give you better performance because it drives your features all the way to 0. Whereas the squared error will tolerate lots of very low weighted features. But people still use it. And people call this L1 versus L2 regularization. That's what they mean. Okay. All right, so now we're going to talk about the kernel trick, which we were talking about before. So here is another data set that I generated. And I don't know, maybe I'll show the code in this. I was going to implement support vector machines, but I couldn't find a good quadratic programming library, and I didn't think that would be very much fun, like learning how to use this random, like I found one, but it was random, and I think it would be a very good lesson. So I did implement this, but I used a machine learning toolkit in Python, Scikitlearn. And I recommend you check out like the space of these kinds of toolkits. There's a lot of really nice ones out there with all these algorithms already implemented for you. Okay, so here is a decision problem. You have, and I generated this data. This is like an artificial data set. I just said if sample some points in this square, if the point's in the circle, it's in class 1, and if it's not in the circle, it's in class 2. So what is my SVM going to do if I just sort of train with the same kind of decision boundary as I did with this one?
I'm trying to draw a line somewhere.
Yeah, exactly. Is it going to work very well? No, it's going to suck. All right, so this is what it happens to do. It just tries to draw a line, but it really doesn't give us very much information because our data doesn't match our assumptions. Okay, a linear classifier in this space isn't going to give you a good classification result because it's nonlinear, right? It's a circle. It's got some x squareds and stuff like that in the data that generates it. Okay, so this happens a lot. Like this is a kind of artificial, but in practice, a lot. What? Okay, a lot of our data doesn't match this sort of nice linear separability criterion. So what we do is, what people do is basically transfer this to a different feature space. So this is my 2D feature space, x1 and x2, and then the y's are coloring with my class. So here's a new feature space. Oh, my commas got stuck up in the exponent. I hope you don't mind if I fix that. Let's see if that worked. Okay. Here's my new feature space. So I'm just going to take in my old feature function x1 and x2, and I'm going to return 3 features instead of 2. x1 squared, x2 squared, and the square root of x1 and x2. So what's that going to look like if I plot it? If I just move my data to that new space? Am I going to be in 2D or 3D?
Oh,
It'll be in 3D, yeah. So my points are going to be transformed, right? So let's take a look at how the transformation looks. So this is it. I'm actually going to run it because then you can see. We can kind of move around in it. All right, so this is it. I'm just going to kind of zoom us around. So this is the same. We just transferred all these points. So here we have this kind of point cloud, and it's this nice conic sectiony kind of thing. Does that make sense? So what do we think about this? If we try to run a linear SVM.
Good.
What's that?
Be better.
It's going to be better. Why is it going to be better?
We can draw a nice plane.
Yeah, right. I can just draw this nice slice. It's linear in 3 dimensions instead of 2 dimensions. But I can draw a nice slice right through my data and come up with a linear decision boundary. And all I did was just do this funky, weird algebraic transformation to my features. And it looks a lot nicer. Okay, and actually I'll make this bigger so you can see it. Running, if we do this, forgot which one I called it. So this is my circles classifier. This is my circles classifier, and I'm just printing out the accuracy. It gets about half of them right in logistic regression, and SVMs do the same thing. But if I convert to this new feature space, and it works for both algorithms, then my accuracy goes way better, right? Like I have this nice separating hyperplane where it slices things out. So everything is a lot happier. So now we're going to talk about So what this sort of means mathematically. So to do this, I actually directly created this feature space. I took each point, I squared it, and made it a little vector, and I made this square root. I can actually show you the code. Right here. All right. So here's what I did. I took the original data set and I just squared it, each one, and made this new space. And then you can run it and you get this higher performance. But you actually don't need to do that. So it turns out, so we were talking about this Lagrange representation where you only need the dot products of the feature. And in general, we have to write it like that. But for specific choices of the way that we mix and match these features, we sometimes don't have to compute this dot product directly. So we can write it, so when people talk about kernels, this is what they're talking about. Instead of writing it as a dot product, we can replace it with a kernel function. And these kernel functions are chosen so that they correspond to a dot product in some feature space. But we've done some math to simplify it so we don't actually have to instantiate this whole big feature vector. So in our circle example, this is what the kernel looks like. It's xm.xn in our two-dimensional feature space squared. Okay? And I can stick that inside my optimizer at training time, and I don't have to go into the feature space. So it's more efficient. Now in this example, it's only 3 features. It's not that big of a savings. But using this, so this is what people call the kernel trick. But using this trick, you can actually use really rich, really powerful feature spaces in more complicated examples and get a lot of power in exchange. So it opens up a space of, it lets you use much more richer feature spaces without paying the cost in terms of the dot product. All right. And there's lots of popular kernels. So when people talk about linear kernels, that's basically saying no kernel. I'm just going to use the dot product directly. You could use a polynomial kernel. That's what we did just now to give you this 3D view of the world. Where is it? This 3D view of the world. A lot of people like to use radial basis functions. So it's sort of how far you are from different key points. Or sigmoid functions. And a lot of the research in machine learning today is coming up with new kernel functions for different types of data. So there was a bunch of papers in computational linguistics using parse tree-based kernel functions because that kind of captures the structure of sentences. Like you have this noun phrase, verb phrase, sentences, kind of this grammar of natural language. And there was a series of papers about how to make classifiers that use these as your kernel function, and that got increased for performance. So the kernel function is how you put more information into these classifiers. Okay. All right. So I'm finishing way early, but that's sort of my take on SVMs. I think I'm going to use a little bit more of the time to just go through the code for how to use the Scikit-learn, and then I'll let you guys out early because I went way faster than I thought I would through this material. So first of all, are there any questions about anything we talked about? Yeah?
Like, kernels are just like a sciencey thing, like they just, like an arty thing, like you pick it, and sometimes it works. There's no, like, pure reason why they pick one kernel over the other.
Well, there are. I mean, you sort of. Yeah.
Yeah.
I mean, the kernel is going to give you something when it matches your data better.
Right.
So just like the features in the first place, when you pick the features as a designer, it matters a lot. Like if you pick bad features, things aren't going to work. So this is another way that you as a designer can inject your knowledge about the domain into the learning algorithm. And that's something machine learning people don't like. So like the purest machine, like what we really want, right, is for us to have to put no knowledge in and just let it play and learn and somehow come up with these structures. And that's why people are so excited about deep learning, because somehow they seem to learn, like there's that Google cat photo and stuff. Like they seem to learn without us having to do as much knowledge engineering. But that's still it's sort of one step in that direction. But in terms of practical applications, most of your time is in making a machine learning system isn't actually doing the math of how an SVM works. It's coming up with good features and good kernels and finding good model parameters. Yeah.
So when you decided your kernel, how do you know where to kind of choose the center? Like, why did you know to put it in the center of that circle? Like, why wouldn't it have been any other points or any other data, piece of data that would become the center of the circle and give you the
So why did I pick those particular? Wow, it's still working. Yeah.
When you projected it into that cone shape,
Yep.
you knew ahead of time where the center of that circle seemed to fit.
Yeah, so this kernel was kind of designed to make this classification problem go really easily, sort of look, really, really nice. However, it turns out that when you, just generally by going from a 2D space to a lot more dimensions, your points are going to spread out naturally, right? And as they spread out more and more, it's more likely that there will be a linear decision boundary. And there's actually, in the book, there's some theoretical results about this. So there's some promises that if you pick your kernel in the right way, it might not be as this is kind of a rigged demo, but it might not be as perfect as this example, but it really will spread things out in a different way that will make things easier to learn. Yeah?
So yeah, when you do your kernel, you can only do that when you already know things about the space, right? Like if you hadn't known that it was distributed around the circle, you wouldn't be able to make that.
Yeah, so for this particular example, that's right. If I hadn't known. But for other examples, especially the RBF kernels, they'll pick these key points in a data-driven way. And that will often let it do kind of the right thing, kind of like our rigged kernel there, without actually us having to put in the data. So it's sort of a, it's trying to do it itself, but it's also making assumptions about the data. So the other take home about all of these different tricks, and also thinking about decision trees and other types of models is basically every single one of these models, there's functions, there's data sets where where they completely fall apart, and data sets where they work well. So identifying the type of data that your data is and finding a model class that matches is a big part of the art of machine learning. So my friend told me once that there's 3 rules for making your machine learning system better. The first one is more data. So just add more data, and you should always be checking where you are on this curve, right? The more data, and then the error, and making sure that you're out here, unless data is really expensive. Sometimes data really is expensive. There's better models. So that's all of these kinds of tweaks. So if I'm using SVMs, is my kernel a good match for the data? Is it separating my training data in a good way? Or maybe my classification problems are a really good fit for decision trees. Or maybe I really need those probabilities, and I should be using logistic regression. So better model. I'll write this down, because this actually has helped me a lot since he told me this years ago. More data. Better models. Anybody want to guess the third one? Yeah?
Better features?
Better features, yeah, exactly. Better features. Better features. Better features. So this is talking to a domain expert or becoming a domain expert and coming up with the, what you actually stick in these graphs. What are your x1s and x2s, and how do they correspond to real world things? And next class we're going to talk about an example of this, and specifically in computer vision. And we'll talk about where the features come from and sort of how that feature engineering process works. So a big focus of research in computer vision right now is better features. Yeah?
Will decision-making trees help you choose better features?
Yeah, so sometimes people work on that. So even these types of algorithms can help you know if features are good or bad, because why could you use that? How could you figure out which features were important for the algorithm versus not, for SVMs or logistic regression? Let's go back to this. Yep.
That's with the weights vector.
Yeah, so you can take a look at your weights vector. So each weight vector, each entry in this W corresponds to a weight assigned to a particular feature. So I can go look inside here and see which ones are good and which ones are bad. And we talked about regularization. So regularization would be adding a bias against big W's, right? So when we talked about this, it's going to want the magnitude of this vector to be small. It's going to want every individual entry to be as small as possible while still minimizing your classification error. So that itself will help you select features. So with the squared error, it's going to give you a lot of really low-ranked features. With the absolute error, it'll actually drive your features to 0. So if a feature weight here is 0, it's saying I didn't use that feature to make my classification decision. The same thing is also true for decision trees, though. So a decision tree is going to be like if feature 1 is greater than 0.2, and then it'll be another one if feature 2 is less than 0.3, then return class 1. It's like this big sequence of if statements. And you can inspect it. You can just see what it's doing to make its classification. And you can also compute statistics about it to see which features are important. Yeah?
When SVM is performing this classification, where does it actually get the weights vector from?
Where does it get the weights vector from? Did I actually write down the training thing? Yes. So we do this argmax at training time. And the output of the argmax is a W and a B. And those are the weights. So I can show you the code for what this looks like. Which one was I? All right. So basically here, I'm pulling out. That's a logistic regressor. But it's the same thing. It's still a W and a V. So I'm pulling out the coefficient, and then doing some math and getting an X and a Y for that line, and then the support vectors, and then drawing the line, and that's what's actually making this picture. So. So when I'm drawing this blue line here versus the yellow line, this one is support vector machines, and this one is the logistic regressor. That's the output of the training process, those actual W's. So one thing I've done to debug these types of systems is made like GUIs so that you can print, it basically prints the feature weight, the feature name, because usually these, in big problems, there'll be a chunk of code for each feature, or maybe the name of the function that computes that feature, and then the value for specific data sets. And like you stare at it, you look at the misclassified examples, you see why they got misclassified, which features were assigned high weight that caused it to make its decision. And then a lot of times, like if you're really digging into it, you'll find there's a bug. Like this feature is computing the wrong thing. So that's sort of working on having a better feature for your system. Or maybe you need more data, and then even if the feature wasn't very good, it would learn, if you had more data, it would learn to discount it. And that's your better features. And I think better models is sort of subsumes better features, right? Like one way to have a better model is by making better features. It's just like a really good way, so it gets its own bullet. Does that make sense? Okay. All right. So basically, this sort of shows the sort of Scikitlearn. There's really nice toolkits for all this stuff now. This is the Python one. You just get your data, X and Y. So here, it's pulling them from 2 different Gaussians with different centers and the same variance. And then this is making the class, so 0s and 1s. And then you feed it into these different models, and then you can plot the different outputs. And there's toolkits like these. There's one in Java called Weka, and there's ones in other languages too. So if you haven't, a lot of times in machine learning classes, like they make you implement them all, and I think that's good because you really understand it. But in practice, it's often better to use one of these toolkits because the optimization's in C and it's really fast and it won't have a lot of bugs. So we're making you implement it actually in your project again so that you can really understand what's happening and what the parameters mean. But I don't, there's actually a problem when I took my first machine learning course is I was like wedded to one of these toolkits and I avoided implementing the algorithms, and I didn't understand them for a long time until I went back and implemented and debugged and really got logistic regression. All right, guys, more questions? No. All right, well, I apologize about the early end for class today, but hopefully it'll be a nice warm-up for coming back after spring break. I'll be around till official end of class time. If any of you guys want to talk about anything, I'm happy to do that.